Welcome to the video today, guys. I've got a very special guest for today's video. I have Professor Muhammad Omar from Harvey Mudd College in Southern California. He has a great YouTube channel called Prof. Omar Math that you guys should check out. It's much better than my channel. So today we're going to talk about, his strategy for writing contest problems. So maybe before we get started, could you tell us a little bit about your experience writing contest problems?
Yeah, so I've had now decades long experience writing for lots of different high school level math contests. So I've worked in both Canada and the US. One of the most notable is the AMC competitions. So for a few years, I was on the AMC 10-12 Problems Committee, which consisted about 8 or 10 people who were sort of in charge of making the problems for the contest. I've submitted problems for the Amy, USAMO, and then currently I'm on the Euclid Math Competition Committee, which is a 12th grade contest in Canada. I've worked on the Canadian Open Math Challenge, and then a lot of other contests here and there. So I've been involved with this for a very long time. It's something that I'm interested in for a lot of different reasons, maybe even different than what usual people are usually interested in for, which you'll learn about in the video today. So yeah, it's great to be here.
Yeah, well, thanks again for coming. So, we're going to do two main things today. So, we're going to go through a couple of existing contest problems and talk about perhaps what the motivation the authors had for writing these problems, like what particular parts of math, as well as maybe some strategies for getting off the ground solving them. And then after this, we'll talk with Professor Omar about his strategy for writing some problems. And I think he has some really nice insights into his unique approach for writing problems. Okay, let's get into it. Okay, so the first problem I thought we'd look at is from a Belarusian test. I think this is a team selection test. And I like to look at it. There's like this symmetry between the variables x, y, and z. So our goal is to find all natural numbers n such that if we have x plus y plus z equals 0 and this product x, y, z equals 1, then this like power sum, this nth power sum of the three variables is constant. So what's the first thing that jumps out to you about this problem?
I think is exactly what you said. You kind of see symmetry, and I think a lot of times with these various sort of Olympiad level type problem sets, you have a play on some type of symmetry in the variables. And as soon as you see that, there are sort of some natural things to hop onto. So if we think about this from the perspective of the person who wrote it, they're probably familiar with all these tools, and then they try to build their own spin on those tools to create something that might be a little bit novel. I think another thing too is with these types of situations, for somebody who's trying to actually solve the problem, it tends to be the case when you're asked for like polynomials with certain like variable degrees to determine when some certain phenomenon happens is usually almost all the time or almost never. So that's sort of like from the perspective of somebody trying to solve it. But from the perspective of somebody thinking about actually creating this problem, I think what they thought is they have familiarity with how symmetric polynomials work and how they're related, and then they try to craft a problem based on that. I think another thing which would probably resonate with a lot of the audience is this idea of Vieta's formulas. And these are formulas for the roots of or relationships between the roots of a polynomial and their coefficients. And this also sort of screams that out, where you can imagine x, y, and z being roots of a polynomial of degree 3. And we have the information that the sum of those roots is 0 and the product is 1, which tells us something about the second degree coefficient and the constant coefficient, and then you can use that to figure out things about powers of sums of powers of the roots.
Yeah, one thing I really like about this problem is that we've got two symmetric polynomials, this xyz and this xyz, that are in three variables. And if you like know anything about symmetric polynomials, you generally need one in each degree up to the number of variables you have to know everything about the situation. So here we've got a linear symmetric polynomial and a cubic symmetric polynomial. So to know everything about the situation, you would need to also have a quadratic symmetric polynomial. And then if you had a quadratic symmetric polynomial, then you would be able to essentially find any expression in x, y, and z. So anything like this would always be a constant. So here you're like given almost enough information to know everything, but not quite enough information to know everything. And so the real game would be to figure exactly what we're missing.
And it's interesting because there's this thing that one learns if you take sort of an algebraic combinatorics course sometime in maybe an early graduate school, or maybe in the rare case late undergrad, where you learn all about how to switch between certain families of symmetric functions and other ones. So the standard symmetric functions like x plus y plus z, or the sum of products of pairs, or sum products of triples, etc. These are like elementary symmetric functions, and they form a basis for all symmetric functions, meaning you can write a symmetric function in a bunch of variables as a polynomial in the elementary symmetric functions. The same thing happens with power ones: x plus y plus z, x squared plus y squared plus z squared, x cubed plus y cubed plus z cubed, etc. You can write any symmetric polynomial in terms of those. And then there's a transfer between the two bases, kind of like if you're doing linear algebra and you have a basis for one vector space as another, there's a change of basis matrix. There's a standard way to go from the basis of power symmetric to elementary, and all the other bases as well. So I can imagine if somebody is like a practicing mathematician trying to come up with an interesting problem, what they probably thought of is, hey, I know how these bases change, but we don't have the full information. Like you said, we're missing a quadratic part for the x, y, z. So then what degrees of freedom do I have when I actually try to do the basis change?
Mhm.
And that's probably like the insight that they had, and then they could turn it into an interesting problem at the sort of high school level where you don't have all of those linear algebra tools.
Right. So just to be really specific, you would do a basis change from this elementary symmetric polynomial basis to this power sum basis like this over here, and you would see which terms in the power sum basis don't use that quadratic term from the elementary symmetric polynomial basis. Yeah.
Exactly. And of course, like for a high school student or like an interested college student, there's no way that they're necessarily thinking in this light, right? But the real thing is like, how are the problem creators thinking about this? Now, I know from my perspective, even sort of as a problem creator who's actually like a practicing mathematician, a lot of the times my problems come from sort of these insights that are farther in mathematics, but that can like be explored, explained, and like um, sort of shed light to themselves, like in these contexts that are much more sort of like in the problem solving realm.
Yeah. Great. Should we move on to the next one?
Yeah, sounds
Or
great.
actually, before we move on to the next one, do we have a quick guess as to what the answer is?
Um, I actually like played with this a little bit. And I originally had the guess that this is gonna work out when n is a multiple of three. Um, I have a way of figuring out that it is the case that x cubed plus y cubed plus z cubed is constant, but I haven't explored enough to see what happens when n is larger than 3. So I think playing around with when n is larger than 3, but a multiple of 3, I might be able to discern whether or not my guess is right. So I don't know
Yeah.
yet. Um,
Yeah.
yeah.
So I think that's a good guess. And then I think if anyone watching wants to play with it, this is like a kind of a good place to start this guess towards this problem. I bet for in a non-multiple of 3, you could probably just play the game where you pick explicit values of x, y, and z and show that you can get different values of, for instance, x squared plus y squared plus z squared. I bet it wouldn't be too hard to just pick some explicit values of x, y, and z to figure out that the square power sum polynomial is not constant. That's of course like not towards an answer, but it would at least give you some motivation towards this guess.
Definitely. I'll say one last thing, which is sort of, I'm not sure if this is an approach that'll work. I don't know. Um, for some reason, my intuition is telling me that there might be an approach where you sort of think of X, Y, Z as complex numbers written in polar form, and it'll reveal something geometric that's going on. But I'm not sure.
Oh yeah, this is like motivated by the fact that x plus y plus z is 0.
Yeah, exactly. So
Yeah,
like the
so
if you write the vectors, they sort of like balance each other out, and then
mhm.
something's going on with the powers. Yeah.
Yeah, I like that a lot. Okay,
Yeah.
so maybe we'll move on now. Okay, so for
Yeah.
the second one, it's from the same team selection test, and this has to do with a binary operation. So we have a binary operation star on a set R, and it satisfies two conditions. So the first one is for all A and B in R, there's a unique X in R, where we would generally write this as multiplying X and A, but here it's the star operation. So if you were to do X star A, you get B. And then in that case, we write X is A over B, kind of motivated by multiplicative notation. And so that's one condition that this satisfies. And another condition it satisfies is that the um, operation distributes over itself. So unlike operations that we are familiar with, they do not distribute over themselves. So this brings us to two questions. Maybe we'll talk about them one at a time. So the first one is star commutative? So maybe first of all, like, where do we think this problem came from? What was the motivation behind the problem author? And then we could talk about guesses for these solutions.
Yeah. So we'll just remind commutative means you can if you multiply A star or A star B, that's the same as B star A. And so these type of exercises are like really common in introductory course on abstract algebra. So I would not be surprised if the person who was creating this or who created this had maybe some experience thinking about or teaching like a introductory group theory or ring theory class and was trying to come up with like an interesting problem that tests like the mechanics of understanding how binary operations work and what it means to have the concept of like a unique uh, thing that you multiply by to undo multiplication. So that's my sense is they sort of started with this sort of natural thing that happens in abstract algebra, and then they tried to tweak it a little bit to be a little bit more weird. And then we're like, oh, what happens if I do this? Does this turn out to be commutative? And probably had like a long string of equalities that got them there.
Mhm. Yeah, that seems right to me. I would imagine that someone was writing down a homework set for their abstract algebra class, probably before the definition of a group or a ring was given, and the game was just to play around with some binary operations, and
Totally.
then a rabbit hole was descended into until this problem was found.
Yeah, and I think, I know a lot of times when you're faced with a question like number one, where you're asked, is the operation commutative or not? You're sort of simultaneously doing two things. You're like trying to find out whether it is, but also skeptical and thinking maybe it's not. And this causes frustration because you don't necessarily know what path to go to. But in this case, I actually think it's a natural question to ask because my suspicion is that the person who created this did not know the answer and then explored given these two phenomena and then eventually got to something. So they're kind of giving you the experience that they actually genuinely had themselves.
Mhm. And what do we think? Do we think it's commutative?
I think it is. I haven't played around enough yet to know. The reason I have the intuition is just imagine if it wasn't, the amount of work that one would have to go through to refute it. You need a binary operation defined concretely on an arbitrary set, and then you would need both conditions one and two to occur.
Right.
It's sort of like a lot, there's a lot there. And if you want to think of an example that's natural, like something like picking R to be like, the rational numbers or something without zero or something like that, and then picking multiplication, then you're almost kind of toast and trying to get something like number two. So it's sort of it's difficult, yeah, to come up with
Yeah.
a counterexample.
Yeah, I would agree with that. I would think the nicest sort of set you could make and operation that satisfies these rules is I wouldn't even think of what the nicest set would be that would have an operation with these rules. Maybe you would have a singleton or a doubleton, and then the operation would just be like A star A is A. Um,
Yeah.
Anything more complicated, any larger set, and it would be a nightmare to try to figure out some sort of multiplication table that would
Yeah,
satisfy
too much.
these
Way too
rules.
much.
Yeah. And likely playing around with it, I bet the commutativity falls out fairly quickly, especially since this is a two-part question. Generally,
Mm.
on these types of exams, the first question falls out fairly quickly.
Mm.
Um, what do we think about the second?
My sense is the second one is probably relatively okay to do. I think the thing that's sort of challenging about it is reading it right.
I agree.
So yeah, so especially reading the right side. The right side has a lot going on because the division symbol comes with this statement of having a for all statement and then a uniqueness and existence statement in it. So, but these are like, but then you have a quotient of a quotient. So it's like a embedded for all stuff.
Hmm.
And so,
Hmm.
in my sense, it's sort of the real challenge is really being able to read what does the right side even actually mean. That's sort of, I think, what's being really tested.
I totally agree. And this semester, I'm teaching a proofwriting class, and I've just been preparing it. And I just prepared the section on existential and universal quantifiers. And this second question seems just like maybe hidden isn't the right word, but I'll use it, a hidden masterclass in working with existential and
Yeah,
universal quantifiers.
exactly, exactly. Yeah, definitely. It's interesting. Yeah, it's creative. It's a different, I think it's sort of like it's almost like a Olympiad logic question, which is like not a thing that really happens. You know?
Right, right,
Uh,
right.
yeah, yeah,
Okay, should we move on to the last one?
yeah. Yeah, let's do it.
Okay, so I really like this last problem. So it's a mixture of number theory and a functional equation. And so we've got a function, or we want to determine all functions from natural numbers to natural numbers, where for all natural numbers n and primes p, we have p divides f of n times f of p minus 1 factorial. And so the factorial is only acting on the f of p minus 1, and then plus n to the f of p. So what do we think the motivation is behind the author of this problem?
Yeah, so 2020 was the pandemic, and this looks like pandemonium. So maybe that's part of the motivation. Um, but yeah, I think functional equations are sort of this funny landscape where in many situations, the functions that arise that satisfy a particular condition are like almost always the quote unquote easiest functions or simplest. So a place to typically start with these for the problem solver is to pick a function that's relatively simple, like an identity, like f of n is n, and then at least starting there to see what's going on, which in this case would make sense to start with because the object is being divided by p is like some complicated thing. And
Right.
then yeah, so if you do that, then the expression on the right hand side I think becomes n. Yeah,
So almost always for functional equations, the solution is the identity function.
yeah, it sort of depends on the context. So now, right here, we have a function from the naturals to naturals. There are a
Right.
lot of times when it's like the functional equation is something like f of something equals something else and some
Hmm.
weird expression. And then almost always it's like, may not always be the identity, but I feel like there's a natural candidate for a function as a first choice. Like maybe it might be a linear function. You just sort of see quickly that
Hmm.
a linear function is going to work. And then
Right.
almost always it's like, that's the thing. Yeah. Now, in this case, if you set f of n to n, then the right hand side, I think, becomes n times, maybe we should write it. So, like, it's
Yeah.
n times the quantity p minus 1 factorial.
So we have n times p minus 1 factorial plus n to the
N
p.
to the p. And then if you have like some familiarity with like number theoretic stuff, you're seeing like sort of a few things happen. One is you have n raised to a prime, and there's some divisibility statements on that with primes, and then there's p minus 1 factorial, which also has a thing. So there's the Fermat's little theorem, which says that n to the p is actually congruent to n mod p.
And that's true for all n.
That's true for all n.
Hmm.
And then p minus 1 factorial is always congruent to negative 1 mod p. That's Wilson's theorem. So if you look at the expression we have then, it would be congruent to n times negative 1 plus n, which is 0. So this condition actually is satisfied for this function.
Yeah.
Um, and so if we go back to sort of the theme of our like discussion, right? So our thought is, how do people come up with these problems? You know, I think somebody sort of was thinking like these are some classical number theoretic theorems, Wilson's and Fermat, and if you put them together for all p and n, you get that this expression is always divisible by p. And then
Hmm.
they're probably thinking, okay, well, what if you like change the function in the base and of p to something slightly different? Can you alter things and then still have this divisibility condition happen? And then they probably
Hmm.
played around to try to figure that out, and found out the situations when or when not that happened.
Right. I could see this this expression right here, or showing that this expression was 0 mod p, being like a nice, homework exercise number one after you've
Yeah.
learned, like a gimme, but still, a little bit of a homework exercise, because this left hand side, is a little bit intimidating at first,
Yeah.
before
Yeah.
you've totally internalized these two results. And
Yeah.
then, like you said, like how can we wrap that? How can we wrap this result into a box, which is a little bit more interesting? And in this case, the box is this like functional equation.
Yeah, exactly.
Now I think it's a good idea to talk about what your strategy is for writing contest type problems.
So a lot of times, research actually gives me good ideas for contest problems. So I'm always like thinking in my mind, when I'm working on various research projects, like, oh, is this a cute little piece that I could throw and make into a contest problems? And almost always, this brings about something that just looks completely different than what people have seen.
Mhm. So is
And
it like this? Are the toy examples that you work with to give yourself intuition for these larger problems? Are those toy examples like being molded into the contest problems?
that's a perfect example of one way that this happens, like a sort of little examples of a general phenomenon I turn into some type of competition thing. Sometimes it might be something like the following. There's like a little lemma inside of a paper, so like a small theorem that supports a much bigger theory. And there's a way to turn that into an actual interesting word problem. And so that becomes this whole thing as well. And it kind of becomes really interesting. This happens a lot in like any time I'm doing graph theory related research. Is sort of it's hard to take real graph theory research and change it to contest problems because it's too hard, right?
Right.
But there are little snippets within it. You'll have like little lemmas um, that do translate quite nicely. So one perfect example of this is something like the following. One of the things that I worked with had to do with bounding the size of something called a neighborhood, which is something like the following. You have like an object and it's connected to a bunch of other objects. The neighborhood is the things that it's connected to. And then there are like two neighborhoods, which are the things connected to the things you're connected to, right? And things like this.
Hmm.
And one
Like
of
the
the
difference in your
things
next door neighbor and your down the street neighbor.
exactly, perfectly, right? And so one of the things I was working with had to do with bounding the size of these things based on some phenomena that were going on. And so the way I constructed the related contest problem had to do something with like friends on a social network, right? And sort of like you have your friends and then the friends of your friends. Like how large can that whole thing
Right.
be? Yeah. Yeah,
Yeah.
it's fun. It's really cool. And it brings about like completely novel perspectives as well, like I said.
Thanks for giving us this insight into your process. I'd be interested to know how common this process is versus like other people's problem writing process for math contest problems. I would assume that a lot of people use the same kind of strategy as you. I know that I don't write contest problems, but often when I come up with problems for students to do undergraduate research projects or senior projects for when they're graduating, they come from very simple parts of my own research. So I think at least I resonate with this picking off small pieces of my research towards other like smaller uses, if you will.
Yeah, and I think my experience with the various contest committees that I've been on is that typically a lot of new problems are adaptations of things that have existed already.
Hmm.
And a lot of times people on committees have like a set of ideas that they think are common folklore or knowledge, and then they start by taking those pieces and tweaking them in interesting and somewhat different ways. In my opinion, those those approaches can be great, but they bring in novelty, but not sort of at the stark, blunt way that you might see like with the Minkowski sum problem,
Right.
right? Where you're just like, oh, that's really like quite different. You know what I mean? How do you handle something like that?
Hmm.
And yeah, so I definitely like the approach for that.
So, for instance, the functional equation problem we looked at, is two very, very standard number theory results, probably the most popular number theory results that show up on math contests, just put
Yeah, for
together
sure.
in a unique way. So I could imagine
Yeah.
someone saying, "Okay, I want to write a number theory problem," and then looking at the dozen long list of standard number theory results for number theory contest problems, and then um, putting something together. But your
I've seen
approach
some,
seems not to rely on well-known
yeah.
results for contests, which is nice.
Yeah, it's pretty cool. And sort of the mathematics required, I think a big thing is the mathematics is required to do them is just fundamentally quite different.
Hmm.
You can't sort of use the same standard tools that you're sort of exposed to and whatnot. Yeah, I remember I saw a problem, this is several, probably decades ago now, that where it was very much in the light that you were talking about, where it was a problem that had to do with like cyclic quadrilaterals. So like four-sided polygons that were inside of circles, but then it turned into a number theory problem, and it was sort
Hmm.
of like the person sort of melding like both things together.
Right.
um yeah,
So they probably started with a number theory result and then back engineered it into a geometry result.
exactly. No, to be honest, exactly what happened was something like they had the product of two things equaling like the sum of products of two other things, and it just looked like the statement of one of these cyclic quadrilateral theorems, like Ptolemy's theorem or something, where like
Hmm.
products of opposite sides you add and it's the product of the diagonals.
I think there's probably a place for both. I like,
I think
the
so.
standard problem sets are maybe like easier to train for, but the
Yeah.
problems that you write seem to um, test or challenge creativity a bit more, which is, honestly, 1,000 times more important for doing math, but is often not focused on as much.
Yeah, just sort of and then the melding of sort of all of your different experiences like together in a genuine way where you don't necessarily know what's happening. Like I said, it's like not trainable like
Right.
compared
Right.
to
Yeah.
humans.
Yeah. Yeah.
But
Yeah.
that's the hardest problems to come up with. So that's the thing. Like the way that I see it is if I were to not look at my research for inspiration and I wanted to come up with problems, uh, and the tool that I had was problems that already existed, it would be so hard to come up with something that was novel.
And I mean, your research is in like a great area for the synthesis of these types of problems.
Yeah, exactly.
Yeah. Okay. Well, I think we've done a lot of great things here today. Thanks for being on the channel. If
Thank you.
anyone in the comments wants to give us another idea for something that Mo and I could do together, that would be great. I think we'd be open to doing many more videos together. I just volunteered you for
No
much
problem.
more work.
It's
Okay.
great.
Thanks. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.